I'm going to do another example. This time it's 12.2 on page 600. It says a carbon ion. It's not an electron. We're used to seeing electrons usually, sometimes protons, sometimes alpha particles. This is a carbon ion. I'm going to underline that just to draw attention to the fact that it's a little bit different than what I'm used to seeing. It's not going to be a big deal. Okay, I've got the mass, and if I need the charge, I can probably figure out the charge, but I just want to make sure that I recognize that it's not the properties of an electron or the properties of a proton. He has a positive charge of magnitude 1.6 times 10 to the minus 19 coulombs, enters the region of an external magnetic field of this value, find the perpendicular speed. All right, that's good news. Remember we learned yesterday a new hand rule? We called it the deflection rule. It was used to find the direction of the magnetic force on a moving charged particle through an external magnetic field. Thumb, direction of the particle, fingers in the direction of the field, palm points in the direction of the force. But that rule required the particle to be moving perpendicular to the magnetic field. They're telling me that it is perpendicular here. Okay, so that means that that rule applies. And the equation that I learned yesterday, F is equal to QVB, also applies. Now, the only other situation that we could deal with is if they're not perpendicular, they've got to be parallel. If they're parallel, the force is zero. There is no direction of a force. Parallel, force is zero. Perpendicular, force is QVB, and the hand rule for deflection applies. Anything other than perpendicular or parallel, we don't know how to do that. Okay, this is perpendicular. What we learned about yesterday is applicable. Find the perpendicular speed at which the magnetic deflecting force will balance the gravitational force such that the carbon ion will travel in a straight line. That's a little bit different. Will balance. What is that telling us? Yeah. What's zero? Well, what force is zero though? The net force is zero, right? If force is balanced, then one force has got to be equal to something else. Now, what two forces are going to be equal to each other in this case? What two forces are going to balance here? What are we going to set equal to what? Yeah, Nick? Good. The gravitational force is equal to the magnetic force. Strictly speaking, gravity's got to be down, right? And if they're going to balance, the magnetic force has got to be up. So it's really the magnitudes that are equal, not the actual values, because one's positive, one's negative. You know what? I just want to double check this just to make sure the magnetic force is in fact up. Okay, I'm pretty sure, given the way the question's worded, that it's going to be. We know gravity is going to be down. We presume the magnetic force is going to be up. But like I say, let's just double check that. It's a positive charge. We're going to use our right hand for the right hand rule for deflection. Thumb the direction of the particle, which is into the page. Magnetic field, the external magnetic field goes from north to south. So my fingers are going to be stretched out toward the south. And my palm is going to point upwards toward the top of the page. So gravity is pulling it down. The magnetic force is pushing it up. Sure enough, these two things can balance. Right? Force of gravity is m times g, and if they're perpendicular to each other, the charged particle movement and the magnetic field, then the magnetic force is equal to QVB. What are we looking for here? The perpendicular speed. So let's rearrange that to solve for the perpendicular speed there. V subscript upside down t, whatever you want to call that. So in other words, V perpendicular is equal to mg over q times B. Now again, we got to remember that the mass is not the mass of an electron that we're used to using, but we underlined a carbon ion to remind us of that. The mass ends up being what's given to us, 2.01 times 10 to the minus 25 kilograms times 9.81. Is that 25 or 26? I think that's a 26. Multiply that by 9.81, divided by the charge. It's still the same as the charge of an electron. It means it has one excess proton because it has the ion has a positive charge of 1.6 times the magnetic field strength of 6.32 times 10 to the minus 5. It's a pretty weak magnetic field strength for bar magnets. That's a pretty typical magnetic field strength for the Earth's magnetic field, right? Usually bar magnets are 1,000 times the Earth's magnetic field, but it's still conceivable that that could be the case. All right, let's do the math here. Let's pull out the calculator just to make sure that we can do it together rightly. Say 2.01 times 10 to the negative 26 times 9.81 Let's divide that by, let's use some brackets on the bottom, okay? 1.6 times 10 to the minus 19. And we multiply that by 6.32 times 10 to the minus 5. And we end up getting an error. So let's figure out what we did wrong there. We forgot our times here. So let's insert times. I think that's right now. 1.9 times 10 to the minus 2. How many digits should we be? Should be 3 digits. So it should be 1.95 times 10 to the minus 2. Right? Not crazy hard, eh? A little bit harder than the example in the practice problem that you did yesterday, in the sense that you've got to balance these two things. But listen, if you ever see the word balance, they're telling you what to do. Right? If you ever see the word balance, then set two forces equal to each other. Another word that you could see that would mean the same thing might be suspended. Okay, if this charged particle is suspended, right, then it means that two forces have to balance. If it maintains the same height, then two forces have to balance. If it hovers, then two forces have to balance. And sometimes, certainly in this context, it would be the magnetic force balancing the gravitational force, but it could be a magnetic force balancing an electric force, or an electric force balancing a gravitational force, depending upon the context. Clearly, it's magnetic and gravitational here. Set them equal if you see that word, balance, or something that means the same thing. All right, let's take a look at questions 1 and 2A on page 600, please. Don't worry about question 2B. On Monday, we're going to take a look at this in a little bit more detail so that we can answer 2B a little bit more. So page 600, questions 1 and 2. In addition to that, in addition to page 600, number 1 and 2, we're going to ask you to take a look at worksheet number 11 as well. Tell you what, there's a number of questions on worksheet number 11. Let's do questions 1 to 9. Only questions 1 to 9 on worksheet number 11. Now, that still sounds like a lot, but you're going to see that the first 8 questions are just hand rules. So it's just using that hand rule for deflection, a little bit of practice on that. Question number 9 is the only mathematical question. So you got 8 hand rule questions for homework, and you've got 3 math questions for homework. And you got about 5 minutes to work on them in class.